7, we built the transformer. Self-attention, multi-head attention, the full architecture. Right now, it's an empty blueprint. Every weight is random. It doesn't know language. To go from random weights to a model that understands text, you need 3 things: data, a way to turn text into numbers, and a lot of compute. Let's start with the data. Training data for a large language model comes from the internet. Web crawlers scrape billions of pages and archive them, but raw web pages are messy. Duplicate content everywhere: spam, ads, navigation menus, personal information. So you filter. Remove exact and near duplicates. Strip out boilerplate. Flag low-quality pages. This step throws away a lot, sometimes 90% of what you started with. Then you mix in higher quality sources. Books, Wikipedia, academic papers, open source code from sites like GitHub. For reference, all of English Wikipedia is about 4 billion words. A modern training dataset is 1,000 times bigger. Trillions of words of cleaned, curated text. That's your raw material. The model doesn't read text, it reads numbers. So you need a way to convert words into numbers. One approach: assign a number to each character. A is 1, B is 2, and so on. The alphabet is small, so your vocabulary stays tiny. But the word cat becomes 3 separate inputs. C, A, T. The model has to learn on its own that those 3 characters together form a word. Learning from individual characters is painfully slow. The other extreme: assign a number to each whole word. Cat is 1 number, dog is another. Quick and meaningful. But then what about words like tokenization or entrepreneurship? Every conjugation, every plural, every compound word needs its own entry. Your vocabulary balloons to millions, and any word you haven't seen in training is a complete mystery. Both extremes have problems. The solution is somewhere in between. Subword tokenization. The most common method is called byte pair encoding. Start with individual characters as your initial vocabulary. Scan your training text and find the pair of adjacent characters that appears most often. Merge them into a single new token. Now scan again with this updated vocabulary. Find the next most common pair. Merge again. Repeat this thousands of times. After all those merges, common words like the and is are single tokens. Less common words get split into familiar pieces. Tokenization might become token plus ization. Unhappiness becomes un plus happiness. A word the model has never seen before, say some new scientific term, can still be broken into known subwords. No word is ever truly unknown. After running byte pair encoding, you have a fixed vocabulary. Somewhere between 50,000 and 100,000 tokens. Each one gets assigned a number, its index. When text comes in, the tokenizer splits it into subwords and looks up the index for each piece. A full sentence becomes a sequence of numbers. That's the model's input. But these numbers are just lookup indices. They don't carry meaning on their own. So the model maps each index to a vector, a list of hundreds of numbers that represents meaning. That's the embedding layer from part 7. The model learns these vectors during training. Words with similar meanings end up with similar vectors. Text goes in, dense vectors come out. Now the transformer can process it. You have clean data and a way to turn text into tokens. What does the model actually learn to do? Predict the next token. Take a sequence. The cat, sat, on, the. The model looks at those 5 tokens and predicts what comes next. The correct answer is already in the training data. If the model predicts wrong, you compute the loss, backpropagate, and update the weights. Same loop from part 3. No human labels needed. Nobody has to sit there and annotate anything. Every piece of text is its own training example. The target is always just the next token. This is called self-supervised learning, and it's what makes training on trillions of tokens possible. Think about what next token prediction actually requires. To complete the capital of France is, the model needs to know geography. To continue a code snippet, it needs programming logic. To finish a math proof, it needs reasoning. To match the style of a poem, it needs to understand literary patterns. One simple training objective applied across all kinds of text forces the model to learn an enormous amount about the world. The training loop is the same one from part 3. Forward pass, compute loss, backward pass, update weights. But the scale is completely different. GPT-3 has 175 billion parameters. You can't run the entire dataset through the model at once, so you train in batches. Grab a chunk of maybe 2,000 text sequences. Tokenize each one. Run a forward pass on the batch. For every position in every sequence, the model predicts the next token. Compare those predictions to the actual next tokens. Compute the loss. Backpropagate. Update all 175 billion weights. Next batch. Do this millions of times. One full pass through the dataset is called an epoch. Large models train for many epochs. A single training run can take weeks or months of non-stop computation, and over time the loss goes down. The model gets better at predicting the next token, batch by batch. Why does training take weeks even with powerful hardware? Because the model is enormous. 175 billion parameters at 4 bytes each is about 700 gigabytes. A single GPU has 80 gigabytes of memory. The model doesn't fit on one chip. So you distribute. Data parallelism. Make copies of the model on multiple GPU chips. Each copy processes a different batch of data. After each step, the chips share their gradients and average them. Mathematically identical to one chip doing all the work, but n times faster. What if the model is too big even for one copy per chip? Model parallelism. Split the model across chips. Each one holds a few layers and passes results forward to the next. Tensor parallelism goes finer, splitting individual layers so one big matrix multiplication runs across 8 chips simultaneously. In practice, large training runs combine all 3 strategies, thousands of GPU chips coordinating together. In 2020, researchers at OpenAI published a paper on scaling laws. They plotted model performance against compute on a log scale. The result was a straight line. A power law. Double the compute, performance improves by a fixed, predictable amount. Double the parameters, same thing. Double the training data, same thing. No sudden jumps, no mysterious plateaus. Smooth, predictable curves. You could estimate how good a model would be before spending millions of dollars to train it. You could plan ahead. The scaling curve said, this much compute plus this much data gives you this level of performance. Want it better? Spend more. The relationship was consistent, and so far nobody has found the ceiling. But scaling laws raise a practical question. You have a fixed compute budget. Do you spend it on a bigger model trained on less data or a smaller model trained on more data? In 2022, DeepMind answered this with the Chinchilla paper. For any given compute budget, there's an optimal ratio of parameters to training data. Roughly 20 training tokens per parameter. Earlier models had missed this balance. GPT-3 used 175 billion parameters but only trained on 300 billion tokens. Less than 2 tokens per parameter. Massively undertrained. Chinchilla used only 70 billion parameters, less than half the size of GPT-3, but trained on 1.4 trillion tokens. 20 tokens per parameter. The compute optimal ratio. And it outperformed the much larger model. The lesson was straightforward. You don't just need a big model, you need to train it on enough data. Models like Llama and Mistral followed this insight. Smaller but trained on much larger datasets. As models get bigger, something interesting happens. They don't just get slightly better at the same tasks. New capabilities show up. A small model can finish sentences. Make it 10 times bigger, and it starts answering factual questions. 10 times bigger again, and it writes working code, solves multi-step math problems, translates between languages, and follows complex instructions. Nobody explicitly trained these models to do arithmetic or write Python. They learned patterns in the training data that, at sufficient scale, generalize in surprising ways. The same next token prediction objective, applied at massive scale, produces abilities that smaller models simply don't have. Scale doesn't just make the model better, it makes the model different. Here's the full pipeline. Gather massive text datasets from the web, books, and code. Tokenize the text into subwords using byte pair encoding. Map each token to a dense vector through the embedding layer. Feed those vectors into a transformer. Train it to predict the next token. Millions of batches, thousands of GPU chips running for weeks. Scaling laws guarantee that more compute, more data, and more parameters will produce a better model. At the end of training, you have a language model. It predicts the next token very well. It can finish sentences, generate paragraphs, even write code. But it's not an assistant. Ask it a question, and it might continue the question instead of answering it. Tell it to summarize something, and it might keep writing the original text. It generates plausible next tokens, but it doesn't follow instructions. How do you turn raw text completion into something that actually helps people? That's part 9. From language model to assistant.